Let us discuss about determination of shape functions of various elements. Right. Determination of shape functions now when it comes to shape functions, we have already seen that shape functions are the functions that relates to the unknowns at any point in the element to the nodal unknowns. All right, that we have to remember. Now, determination of shape functions can be done in various methods. First would be with help of polynomial equations, polynomial functions, considering natural coordinate systems, natural coordinate system, when it comes to rectangular elements or the higher nodes of in the rectangular elements, there are concepts such as Lagrange's concept and serendipity. Serendipity concept. Now, as of now, we will start with polynomial functions first. When it comes to shape functions, shape functions of a CST element, that is constant strain triangle element, using polynomial functions. We've already seen that the CST element is the basic element for the analysis. That is a three-noded triangular element. We call that as constant strain triangle. Okay, so let's draw that. A three-noded triangular element. Okay, so let this be node 1, node 2 and node 3, and with the vertices x1, y1, x2, y2, x3 and y3. Let this be the constant strain triangle under consideration. Now let us consider nodal unknowns or nodal variables B. Here nodal displacements are the basic unknowns for the problem are displacements as we have discussed. So let the nodal unknowns be U1, U2, U3, V1, V2 and V3. Let this be the nodal unknowns. Alright, so we will call this as nodal displacement matrix. Alright, now to go forward, we have seen what is the compatibility requirements for the analysis of the problem. So based on that consideration, compatibility consideration, let us consider the displacement model as u is equal to alpha 1 plus alpha 2x plus alpha 3y and v is equal to alpha 4 plus alpha 5x plus alpha 6y. How this displacement model is taken we have already seen from the Pascal's triangle in the previous classes. Alright, so elaborating this a little bit more, let us consider only u first. Alright, now there are three different nodes and in three different nodes we will have u1, u2 and u3 as our nodal unknowns, v1, v2 and v3 as nodal unknowns when the point comes to v. Now taking the same displacement model, u1 will be equal to alpha 1 plus alpha 2x1 plus alpha 3y1. Before that, let us take these as equation number 1. Right. Now, here u2 is equal to alpha 1 plus alpha 2x2 plus alpha 3y2. u3 alpha 1 plus alpha 2x3 plus alpha 3y3. Similarly, v1, v2, v3 can be written. That is alpha 4 plus alpha 5x1 plus alpha 6y1, alpha 4 plus alpha 5x2 plus alpha 6y2, alpha 4 plus alpha 5x3 plus alpha 6y3. Alright. Now, writing this in form of a matrix, this will become u1, u2, u3 which is equal to 1 x1 y1, 1 x2 y2, 1 x3 y3 into alpha 1, alpha 2, alpha 3. Now, for finding alpha 1, alpha 2 and alpha 3, this can be written as 1 x1 y1, 1 x2 y2, 1 x3 y3 inverse into U1, U2, U3. Equation number 2. Now we have a matrix here whose inverse has to be found. So if at all we consider this as X matrix, inverse of this matrix is adjoint of the matrix divided by det of the matrix. Right. On that note, if at all we need to find out det, determinant of the matrix x2, y2, 1, x3, y3, or 1, 1, 1, x1, y1, not y1, it is x1, x2, x1, x2, x3, y1, y2, y3 is equal to 2 into A, where A is the area of the triangle whose vertices are, this is from a basic mathematics, alright, whose vertices are x1, y1, x2, y2 and x3, y3. Therefore, when we write down for alpha 1, alpha 2, alpha 3, this will become 2a into, and we need to find out the adjoint of the matrix. When we find that, the adjoint of the matrix will become x2 y3 minus x3 y2, x3 y1 minus x1 y3, x1 y2 minus x2 y1, y2 minus y3, y3 minus y1, y1 minus y2, x3 minus x2, x1 minus x3, x2 minus x1 whole transpose into our elemental displacement matrix U1, U2, U3. Alright, here considering the terms as A1, B1, C1 and so on, we can rewrite this equation, this whole equation as alpha 1, alpha 2, alpha 3 is equal to 1 by 2a into a1, b1, c1, a2, b2, c2, a3, b3, c3 whole transpose into u1, u2, u3. Where A1, A2, A2, A3 are the terms x2 y3 minus x3 y2, x3 y1 minus x1 y3, x1 y2 minus x2 y1, b1 b2 b3, y2 minus y3, y3 minus y1, y1 minus y2, c1 c2 c3 will be x3 minus x1, x1 minus x3, x2 minus x1. From this, the equation alpha 1, alpha 2, alpha 3 will become 1 by 2a into a1, a2, a3, b1, b2, b3, c1, c2, c3 into u1, u2, u3. Equation number 3. Now, from equation number 1, we know u is equal to alpha 1 plus alpha 2x plus alpha 3y. Now, if this equation is rewritten, u is equal to 1 x y into alpha 1, alpha 2, alpha 3. Taking this from equation number 3, substituting equation 3 in the above equation, what do we get? We get u is equal to 1 x y into 1 by 2a into a1, a2, a3, b1, b2, b3, c1, c2, c3 into u1, u2, u3. Multiplying the terms, we get u is equal to a1 plus b1x plus c1y by 2a, a2 plus b2x plus c2y by 2a, a3 plus b3x plus c3y by 2a into u1, u2, u3. If these terms we clearly see, these terms, I'm naming them as n1, n2, n3 because they are the shape functions. Shape functions are denoted by n, we have already seen that. I'm calling this as shape functions because the displacement in the element is related to the elemental displacement at the nodes. The relation between u and ui is given with respect of n1, n2 and n3. So these are the shape functions of the CST element. So this can be written as u into n matrix into delta E matrix. Similarly, Similarly, it is taken for V also into delta E matrix. So whole, when we are taking it for CST element as a whole, what this becomes, U of x comma y, V of x comma y will be equal to n1, n2, n3, 0, 0, 0, 0, 0, 0, n1, n2, n3 into elemental displacement u1, u2, u3, v1, v2, v3. So this is about shape functions of a CST element using polynomial equations.